Welcome to our lecture on diffraction gratings. Upon successful completion of this unit, you should be able to describe and perform calculations for a diffraction grating and define and calculate dispersion resolving power. Now, two slits are fine, but in the spirit of more is better, which in physics it usually is, we're going to have multiple slits. So suppose we replace the double slits with an opaque screen that has big N closely spaced slits. When illuminated from one side, each of these slits will become a source of a light wave that diffracts or spreads out behind the slit. This multi-slit device is called a diffraction grating. Bright fringes will occur at the angle theta m such that d sine theta m equals m lambda, where m equals the order number, an integer from 0 and on up. The y positions of these fringes will occur at ym equals L tan theta m, where little d is the slit spacing, L is the distance between the grating and the screen, m is the order number, and lambda is the wavelength. Now, these are the same two equations we've had before. We're looking down on a diffraction grating. The light is coming over from the left. There are n slits that are spaced a distance d apart, and this is the top view of the grating as we look down on the experiment. The slits extend above and below the page. We're only showing 10 of the slits here, but a practical grating will have hundreds or even thousands, even tens of thousands of slits. As the light hits these slits from the left and goes through, it is diffracted and spread out just as it was in the double slit experiment. The light will overlap and interfere as due to path length differences, delta r equals d sine theta. It's the same as it was before between the waves coming from adjacent slits. And of course, here is the d sine theta right in here. Okay, so delta r equals d sine, that's this little thing down here. It's a little hard to see, but it's the same. You can go back and look at the other one for the double slit. The lights from the slits will arrive on the screen in phase when the path length difference, d sine theta, is an integer number of wavelengths. And we call that integer the order number. Thus, bright fringes will occur at angles theta m such that d sine theta m equals m lambda, where m is an integer, and it's called the order number. So there will be a bright fringe at the central location, and then there will be y1 on either side. These are the bright fringes, okay, and they'll occur at this situation. For example, light diffracted at theta 2, which would be the second order, the inverse sign of 2 lambda divided by d. This would be the second order diffraction with path length difference 2 lambda. The y positions of these fringes on the screen are ym equals L tan theta m. And of course, you can see this is associated with the tan of this angle here. And that would give you the positions of the bright fringes. For example, the second order would appear at y2 equals L tan theta 2, or L times tan of the inverse sign of 2 lambda over d. Now, be very careful with these equations. With a diffraction grating, you do not want to use a small angle formula, especially for higher order numbers, because diffraction gratings spread these things out so much that you're almost never going to have an angle less than 5 degrees. The angles are going to be in the 30, 40, 50, 60, 70, 80 degree range. So you have to use the complete formula when you're talking about this. Why do we want many slits instead of just 2? Well, it turns out that the wave amplitude of the points of constructive interference is n times e, for n waves, each of amplitude e. Because the intensity depends upon the square of the amplitude, the intensities of each of the bright fringes are I max equals n squared I1, where I1 is the intensity of the wave from a single slit. So as n increases, each of these bright bands gets brighter and brighter, and it's proportional to n squared, roughly. Also, the fringes will get narrower and sharper, which is good because this increases the ability to differentiate between close wavelengths, but it also concentrates light into ever narrower bands. So this is a consequence of energy conservation. The light that would fill the screen is being increasingly concentrated into ever narrowing bright bands. And that's why we use a lot of slits. Diffraction gratings are used for precisely measuring the wavelengths of light. If the incident light consists of 2 slightly different wavelengths, each wavelength would be diffracted at a slightly different angle. Provided that n is large enough, 2 distinct fringes will show on a screen. So double slits broad fringes would never distinguish between 2 close wavelengths. So for instance, here they've got a purple and a blue. These are closely spaced. And you notice the 2 distinct bands. For a double slit, these will overlap so much, you just see one fringe. So the whole idea of this is to split these off and make them easier to see and easier to differentiate. Now, these have lots of uses. They're used to determine the wavelength of unknown light. If you know m, d, and theta, you know the wavelength. Diffraction gratings are used to determine what elements are present on the surfaces of distant stars and galaxies. Each element has a distinct pattern of wavelength that's like a fingerprint for that element. They can also be used through Doppler shifting to determine if the distant stars are moving toward or away, how fast they're moving, rotation speed of the object, and so on. Magnetic fields cause the spectral lines to split. It's called Zeeman splitting. And this can be used to determine the presence and strength of any magnetic field. Strong gravity fields cause the spectral lines to redshift, shift toward longer wavelengths, and that can be used to determine how strong the gravity is on the object. Now, practical gratings with very small values of D displays only a few orders. It is customary to characterize a grating by the number of lines, that is slits per millimeter, and that is little nd here. Be careful not to get these confused. The number of lines per millimeter is simply the inverse of the slit spacing D in millimeters. So D is 1 over nd. Now be very careful to check these units. You can have lines per millimeters, lines per inch, lines per centimeter, lines per meter, lines per nanometer, all different kinds of things here, so be very careful. Now, the width of lines maxima determines the diffraction grating's resolutions. We need to know how wide this line is. We need to know that so we can understand what its ability to resolve separate wavelengths is. So we call this a half width. A half width is 1/2 of the width of the width of the line from here to here. It is the angle between the center of the line at theta equals 0, where the intensity drops off to 0 in the minimum. That's this dashed line here. And this occurs at nd sine delta theta half width, and that equals lambda. Notice that the line itself is twice this. So nd sine theta half width is delta theta half width is lambda. So for small angles and radians, sine delta theta half width is approximately equal to delta theta half width. Now, why is it okay to use a small angle formula here? It's because here, these are so close together. You're not going to have something that, for any practical grating, you want this as narrow as possible. So this is going to be as small as possible. So it's okay to use a small angle formula for this. Delta theta half width is lambda divided by nd. That's a half width of the central line. Half width of any line at angle theta is delta theta half width equals lambda divided by nd cosine theta. Delta theta half width equals lambda divided by nd cosine theta, which equals the half width of any line at angle equal to theta relative to the central axis for wavelength equal to lambda incident on a diffraction grating of n rulings, ruling separation d. N determines the grating's resolution. Large n, which is desirable, equals a narrow diffraction lines, small delta theta half width, easier to distinguish between close wavelengths, and brighter. Now, the dispersion is the angular spreading of different wavelengths by a grating. The units are degrees per meter or radians per meter. Be careful with units. The dispersion by definition is delta theta divided by delta lambda. Delta theta is the angular separation of two lines whose wavelengths differ by delta lambda. D will also equal m divided by little d times cosine theta. Gratings with large big D are desirable and have a larger distance between two emission lines with a given wavelength difference. For a high big D, you want high order number and small little d. So you want the grating spacing to be as small as possible. You want to use the largest order you can get. Big D does not depend upon big N, which is the number of rulings, but it does depend upon the grating spacing, little d. Now, R is the resolving power. It is lambda average divided by delta lambda by definition, where lambda average is the mean wavelength of two barely resolvable lines. Delta lambda is the wavelength difference between them. R equals N times M. We usually want high R, so you want lots of N, lots of rulings, and or a high order number. Now notice there's a theme here. Big N is good. Here we're going to compare the dispersion versus the resolving power of three different gratings. Gratings A, B, and C. And grating A has an N of 10,000 lines, a distance between the lines, line spacing of 2540 nanometers, an angle of 13.4 degrees, a dispersion of 23.2 degrees per micrometer, and a resolving power of 10,000. B has 20,000 lines, but the same line spacing as A, so it's got 2540 nanometers for line spacing. The angle is the same as A, 13.4 degrees. The dispersion is the same as A, 23.2. The resolving power is much better, 20,000. C has 10,000 lines like A, but it has a narrower line spacing. It's only half of what A and B are, so it's 1360. Its angle is now up to 25.5 degrees. The dispersion is up to 46.3, but the resolving power is still the same as A, 10,000. Now here's some of the pictures they may have made. Now don't confuse dispersion and resolving power. Gratings A and B have the same dispersion D, while gratings A and C have the same resolving power R. Note that the lines in B has a higher R, are narrower and sharper than the lines in A or C. Note that C, which is the higher dispersion, has a greater angular separation between the lines than either A or B. Now, these are just about everywhere. If you have a credit card or a debit card, and you look at the logo on the credit card or debit card, and you rotate the card a little bit, it kind of flashes at you. That is a diffraction grating. It's embedded in the device to produce virtual images that vary with viewing angle. Gratings produce hundreds or even thousands of diffraction orders and are so complicated to design that they're extremely difficult to counterfeit, so it makes them very good security devices. They're used in credit card logos and on money to prevent counterfeiting by Xerox copying, because Xerox copying requires a real image to copy. You can't copy a virtual image. Copy machines don't see them or reproduce them, but our eyes and brains do, so it makes them very useful. Now, this is another place they're useful, a grating spectroscope or a spectrograph. This separates different wavelengths or colors of light into distinct diffraction lines. And this is what it might look like. Here, what comes out, these are the lines. Different colors of wavelengths of light. Okay, probably due to some chemical. This is used to study chemical compositions, including those in distant parts of the universe. It can be used to measure Doppler shifts, which will determine the relative motions of stars or galaxies. It also is used to determine whether they have strong magnetic fields, the strength of those magnetic fields, how strong the gravity is. This is basically the way we know about the universe. Now, there is also such a thing as reflection gratings. Most diffraction gratings are manufactured as reflection gratings because it's easier to do. The interference pattern is exactly the same as the interference pattern of light transmitted through slits. All they do is they basically have they make the surface kind of rough here, and they have it's mirrored. It has a bunch of different lines. These are the line width is right here. You can see this on DVD or CDs. It will show colors because the pits and holes in the shiny reflective surface embedded in the plastic discs act as a reflection grating for visible light. And if you'd rotate the angle that you see a CD at, it'd get those pretty colors. Now, another source of such pretty colors are natural reflection gratings. In a feather, there are nearly parallel rods of melanin, which act as a reflection grating. Many insects also have reflection gratings in the form of tiny ridges on their shiny exoskeletons. The colors are vary with the viewing angle, making a beautiful display. It also makes it very hard to counterfeit an insect or a bird feather. Not that anybody would want to. Okay, we want to measure the wavelength of sodium light, and you should be doing these at home before you view the video or come to class. Sodium light passes through a diffraction grating having 1,000 slits per millimeter. The interference pattern is viewed on a screen 1 meter behind the grating. Two bright yellow fringes are visible 72.88 centimeters and 73.00 centimeters from the central maximum. What are the wavelengths of these two fringes? The physics of this, of course, is a diffraction grating. The knowns and unknowns, we know the ND, which is the 1,000 slits per millimeter. We know L, which is 1 meter. We know Y1, which is 72.88 centimeters. The other wavelength is it appears at Y2, that should say Y2, of 73 centimeters. And we know the order number is 1 because it's the first order number. And what is the wavelengths? The formula are D sine theta m equals m lambda and ym equals L tan theta m and D equals 1 over nd. Okay, so I repeated those knowns and unknowns. And we know that ym equals L tan theta m. So theta m equals the inverse tan of y1 over L. And we can also write a similar formula for y2. And we also know that D sine theta m equals m lambda. So lambda equals sine theta m divided by m and D. Now we're only interested in the first order number, so we can drop the m. Let's be very careful with units on this. Now whenever you take tangent, inverse tangent, a sine, cosine, anything like that, you have to make sure the units completely cancel out. If they don't, you're going to wind up with something weird. So you have to be very careful. I chose to put both of them in centimeters. So this is the L, which is the 1 meter converted to centimeters. Here is Y1, and that one comes out at 36.08 degrees from the central maximum, and at a distance 72.88 centimeters on the screen from the central maximum. Similarly, the other one comes out at 36.13 degrees, and at a distance from the central maximum on the screen is 73 centimeters. And now calculate the wavelengths by plugging it into this. We have sine of 36.08 degrees divided by 10 to the minus 6 inverse meters. And of course, this is the m is 1, and this is ND written in inverse meters. So that's where that comes from. So the wavelength is 589.0 nanometers at this position on the screen, 72.88 centimeters. The one is at 73 centimeters from the center of the screen is at 589.6 nanometers. Now notice, do not round off in these. Carry all the digits till the end. If you round off, you can wind up getting yourself in trouble. Also make sure that you have your calculator set to the proper thing. and make sure that all the units cancel out correctly. If you don't, you're going to wind up with a problem. That's where people make mistakes in these. In a laboratory experiment, a diffraction grating produces an interference pattern on a screen. As the number of slits in the grating is increased with everything else, including the slit spacing, the same, then what's going to happen is that the fringes will stay in the same positions, but they will get brighter and narrower. So what you're doing is you're increasing n. And notice the intensity is proportional to n squared. So it definitely gets brighter. And they will also get narrower. Visible light of wavelength 589 nanometers is incident on a diffraction grating that has 3,500 lines per centimeter. At what angle with respect to the central maximum is the fifth order maximum observed? Be very careful with this kind of question. It turns out that you cannot observe a fifth order maximum, and here's the proof. D sine theta m equals m lambda, so D equals 1 over nd, and we plug this in. So sine theta m will be m lambda times nd. This is the fifth order maximum, and here is the wavelength that we're trying to observe. Here is nd, converted to lines per meter. Again, be very careful with units. Make sure they cancel out. Notice that it's a number greater than 1. You cannot take the inverse sign of a number greater than 1. If you get a number greater than 1, you probably either have a very high order or you've made a mistake somewhere. So make sure you cancel units and make sure you check this. In which one of the following cases does the dispersion of a diffraction grating increase? If you decrease the spacing of the grating lines. So big D equals m divided by d cosine theta. As you decrease little d, big D increases. Also, d sine theta m equals m lambda. So as lambda decreases, sine theta m will decrease, and cosine theta will increase. So big D also decreases. Big D, of course, being the dispersion. Two monochromatic beams of light, one red and one blue, are directed to the same spot on the diffraction grating. The resulting diffraction pattern is observed on a screen located a short distance behind the grating. Which of the following best describes the observed pattern? Well, what you're going to see is in the center, the central maximum, both colors are going to overlap each other. It could be a blending of both colors. And if you add red to blue, you're going to wind up with purple. So what you want to look for here is the central maximum appears to be purple. Then all you have to do is figure out which of these two it is, eliminates all the rest. Well, it turns out blue, having a shorter wavelength, is diffracted to a smaller angle than red. So it's going to wind up B. The central maximum appear to be purple. The maximum on each side will alternate blue, then red, then blue, then red on both sides. And you can get this from this. D sine theta m equals m lambda. Both colors are blended together in the central maximum. But blue has a shorter wavelength than red, so the next line on either side of the central maximum will be blue because theta blue is going to be less than theta red. So it'll be purple, then blue, then red, then blue on both sides of the central maximum. Thank you.